So, good afternoon, everyone. Today we have this meeting here on this and the distinguished professor and vice chair of the faculty.
Maybe you can talk to us
Okay.
because
So
when
oh,
those who are online, they can't hear.
Okay. Okay. So he did his PhD from State University, New York, Stony Brook, and then uh, postdoctoral associate in Cornell University. After that, he moved to University of Maryland, and he joined as assistant professor in University of California, Davis in 1989, and then he's continuing there, and he's fellow of Institute of Physics, fellow of American Society, many awards and clubs, and he is one of the most well-known person in frustrated magnets. In fact, many of the things which I have learned from his paper, and it would be great to have Professor Rajiv Singh here, and he'll be giving two lectures on frustrated magnets. The first lecture is going to be quantum spin liquid. He'll give an overview of that, and the second part is going to be on 6, and there he'll be talking about pyrofluor, antifluor, magnet, spin ice, spin liquid, and order by disorder. And with that, I'll invite him for
Thank you. Okay, yeah, I'd like to thank Rajiv for inviting me here. I mentioned to him that my previous visit to the institute was time in the 1990s when the birth centenary of St. Bose was being celebrated, and at that time the institute was barely being built. We were having our meals basically on the floor, on the floor and on the top, the roof. Basically, that was everything was under construction at the time. And one of the keynote speakers was Professor A. Mitra, who was my professor at Delhi University. He gave a really inspiring talk about S.N. Bose and Einstein. I look forward to the archives here. The director has told me that they have a beautiful archive of S.N. Bose. So my talks, the two talks really are both continuations of each other. They are mostly by way of a review of the theme. I'm also giving a talk tomorrow at IACS, which is more related to recent work. So today's talk is about quantum spin liquids, and the outline for the talk is as follows. I'd like to begin with the general question, answer what is a quantum spin liquid? Try to explain why this is a macroscopic quantum state of matter. One should really think of this as a state similar to superconductivity or actual quantum Hall effect. So it's really another system in which macroscopic quantum effects are important. Basically, one can illustrate a very important model, toy model is the toric code model. I'll briefly talk about that, and then we'll talk about how can we observe such a state? What are some of the effects? What are some of the important signatures, macroscopic signatures of such a state? And I'll discuss three classes of materials where people have been looking for such macroscopic state. And a fourth one I'll discuss tomorrow, basically, and then end with a summary and question. So I think it's fair to call it not what is a quantum spin liquid, but rather what are quantum spin liquids. And even though this concept has evolved over the years, I'd like to begin with a historical perspective. Basically, the whole subject was started by Phil Anderson, where he gave the concept of resonating valence bonds. So first of all, if we have a frustrated magnet, which I assume most people are familiar with, which means that we anticipate Sorry, I did not- Maybe you can do that by next. I should really call it what are quantum spin liquids, because there's not just one particular state, but rather a whole family of states that we can call quantum spin liquids, which have interesting macroscopic quantum properties. Historically, the subject really started with Bill Anderson's notion of resonating valence bond. So frustration is when we have exchange interactions which compete and cannot be satisfied simultaneously. So this leads to large ground state degeneracy. So for example, on a triangle, if we have antiferromagnets, out of the with spin a half, so the spins can point up or down. Out of the 8 possible states, 6 of them are basically ground state. If we have a triangular lattice Ising model, this is exactly soluble model using Onsager's solution, and it was first shown by Wannier that zero temperature is the critical point for this model. There's no finite temperature transition, and there is about 50% of the total entropy still present at zero temperature. And in fact, if we have the Kagome lattice Ising model, then there's a finite correlation length all the way down to t equals 0, and the entropy that is retained is almost 72% of the total entropy. So basically, frustration leads to large degeneracies of the ground state. And when we add quantum fluctuations, then Anderson proposed that basically the ground state can now become a macroscopic superposition of these states. So in particular, his idea was that spins, when they are coupled antiferromagnetically, they like to form singlets or valence bonds. And the actual ground state, rather than being a particular valence bond configuration, is really a linear superposition of a large class of valence bond configurations. So he called it a resonating valence bond system. And it was recognized by Anderson right away that such a state, the most interesting property of such a state would be fractionalization, in the sense that if we considered a fixed valence bond configuration, then if you pick an up spin, or if we convert a singlet into a triplet, basically the two spin a halves, if you excitation, will be bound together, because as you try to move them away, you will be breaking a lot of these valence bonds. Whereas if you have a resonating state and you fix the spin to be up, the other spins would relax around that state, and so the excitation in this case would be spin a half. We call such an excitation a spin on. Whereas a spin flip usually is a spin one excitation. Such an excitation would be called spin on and will carry spin a half. And basically, this large scale resonance is absolutely crucial to the system being able to support such an excitation. That was, I think, well understood by Anderson. From an experimental point of view, if we want to look for such a system, I guess obviously we don't want something that robustly orders magnetically. And Art Ramirez, he came up with this thing called the frustration parameter. That is, if you measure the inverse susceptibility, you can get the Curie-Weiss temperature. In an antiferromagnet, that would be negative, or that will come on the negative, have a negative intercept over here. And then if the system orders at the Néel temperature, and if this ratio T Curie-Weiss T Néel is, let's call it F, if this F is very large, that means that the system doesn't order robustly and perhaps is close to becoming a quantum spin liquid, where perhaps there is no long range order at all. Okay, so as I mentioned, the concept of quantum spin liquids has evolved over the years, and now we know that the absence of magnetic order is not really the defining property of a spin. For a long time, people thought so, but that is not the defining property of a spin liquid. What we really need is this macroscopic quantum entanglement. It is a macroscopic quantum phase that has interesting macroscopic quantum properties. states. And so it can even be magnetically ordered and still have this property. So, and it may not be magnetically ordered, and it is still not a quantum spin liquid. So, for example, a dimerized state is not a spin liquid. So, there are models where spins form singlets with fixed neighbors, like in the Jungard-Bush model. And such a system is not a quantum spin liquid. Nor is this, again, broken symmetry may or may not be present in a quantum spin liquid. So let's talk about what exactly is a quantum spin liquid. So to see that, let's first look at this very, very important toy model. A lot of people that had been working on quantum spin liquids, yet a definitive model in which you can see the exotic properties that could be solved exactly was not available until the work of Kitab. So a historic code model is a very nice model in which one can see basically what a quantum spin liquid is, and it's even frustration free. So even frustration is really not necessary. So what is the model? The model basically is a gauge theory. It's a Z2 gauge theory, but it consists of half integer spins sitting on the bond centers, let's say, of a square lattice. One can define it in various ways, but let's consider it in this particular way. And there are two types of interactions. The first interaction is associated with a star. And so a star basically means it's around a vertex, there are 4 spins. And it's an interaction that involves a product of spin operators on these 4 spins. Basically, you'll see it's going to be a sigma x operators. Okay. So basically, all these A sub s obviously commute with each other. Whereas there's another interaction associated with all the plaquettes. Okay, and in that case, it's a product of all the sigma z's of the spins, 4 spins around the plaquette. And you can see that all these A's and B's actually commute with each other, because even though individual sigma x may not commute with individual sigma z, because this involves 2 sigma z and this involves 2 sigma x, they always share 2 with each other, they all commute with each other. So they all commute, their squares are equal to 1. So in fact, it's trivial to write down all the eigenstates of the system. So our Hamiltonian is very simple. It's a sum of terms, and each term can take values plus or minus 1. They all commute, and so we know all the eigenstates. So basically, each one is either plus or minus 1, and we know exactly what their energy is going to be. So what makes this interesting? Well, first question to ask is really how many ground states are there? So you might think that okay, let's have a construction of the ground state. So the ground state of the system is, for example, let's take a state which is ferromagnetic in the x direction. So all the spins, let's say, are pointing in the x direction. Okay, so the state F sub s corresponds to one where all the spins on all the bonds basically are pointing in the x direction. So that obviously satisfies A sub s equal to 1 for every star, because around every star you take the product of plus 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 plus, it's a plus 1. And then what you do is you use this projection operator. So the projection operator is defined again in terms of this plaquette operator. Q sub p for a plaquette is 1 plus b sub p over 2. So it projects out the component which has b sub p equal to minus 1. It will zero it out, and it will give you a state which must have q sub p equal to 1. Which will have b sub p equal to 1. So if we do this for every plaquette, then the resulting state obviously will have all the A sub s equal to 1, because these guys all commute with A sub s. So A sub s is still equal to 1 for every one of them, and b sub p is also. So we have an explicit construction of a ground state of the system. The question is, how many ground states are there? Might think that I could start with some other state over here. So let's start with everything ferromagnetic except, let's say, this, 4 of these let's say, being anti-ferromagnetic or something like that. You could imagine which still satisfies the condition that all the A sub X's are 1, and you do this projection and you still get a ground state. But they are actually not different ground states, because you can easily see that Q sub P has this property that Q sub P times B sub P, you multiply it out, since B sub P square is just 1, is just Q sub P. Okay, so you could start with any state over here which is simply related to this ferromagnetic state with any number of plaquettes flipped. It will still give you exactly the same state over here. It doesn't give you a different state. The only way to get a different state is one where this still satisfies A sub S equal to 1, but cannot be gotten from the previous state by local application of this flipping of the spin one placket at a time. And those really correspond to the states where you have you could, there are only 4, there are exactly 4 ground states on a torus, for example, if we apply periodic boundary condition. And they differ basically by whether or not the product of this sigma x variable on this loop is +1 or -1, and whether the product on this one is +1 or -1. So there, I'm assuming that you have even number of spins in both directions over here. So basically, there are only 4 ground states, and it depends only on topology. So first important property of these spin liquid states is that there's a topological degeneration. Immediately begins to look like the fraction point model. Yeah.
For understand that story code model is where the spin is not really observed because it's not a gauging variant also. So I still call it a spin liquid phase, or is it a bit of a different phase?
It's a spin liquid. It's still it's a model that supports the kind of excitation that we are interested in.
So you're more like excitations.
Yes.
Well, also it has honeycomb model, but spin
I'm going to talk about that model too. Yeah.
But spin liquid are observable. They are.
Yes.
So should we distinguish these from?
Well, all of them. So all these states that have interesting macroscopic quantum properties would be called spin liquid quantum. Whereas something which is dimerized is not.
Because it's a product state.
Yeah, anything that we'll come to that. That is the final definition. Okay, so what is interesting, of course, is another property of such a state is that fractional excitation must be created in pairs. So obviously, let's call the excitations where A sub S equal to -1 an electric excitation or an electric charge, and a state where B sub T is -1 as a magnetic charge or magnetic excitation, because remember, each of these can be +or -1, and that would be an excitation. But you cannot really create such a state starting from the ground state by itself. You must create this in pairs. So if you apply any local operator, like apply say a sigma x operator, sigma z operator on this bond over here, you're basically going to create. Let's see. So I apply a sigma z operator. Sorry, at this site over here. That will, it will always create a pair. So if you flip this over here, that would mean that for this bond, the A sub S would be -1 for this one as well as for this one. So you can only create these things in pairs, and you can separate them as far as you like, but nevertheless, you cannot really create an individual one. And similarly, the magnetic excitations can also be only created in pairs. And a third type of excitation is a bound pair of these electric and magnetic excitations. And
is there a reason for one as an
there's no particular reason. It's just a convention.
magnetic.
There are no real charges over there. So I think either one could be called electric or magnetic. Convention. Okay, but what is interesting again in this model, without going into the details, is that there is interesting mutual statistics. So these electric objects, when you take a magnetic object around an electric object, uh, basically you find that it picks up a phase factor, and in fact this bound pair acts like a fermion. Okay, it has the statistical fermion. So the reason for discussing this model was to point out that this is of course an exactly soluble model, that fractionalization. So this quantum spin liquid has interesting kinds of excitations which have interesting statistics. They are fractional in nature because they cannot be created individually. They can only be created in pairs. And basically, they have such a state is only possible when you have macroscopic non-local entanglement. So people have in fact talked about how one could use such a state for quantum. Okay, and perhaps the people are already familiar with this. One can basically quantify entanglement simply by considering a state of, say, a system consisting of two parts, dividing a large system into two parts A and B, and looking at the wave function of the overall system, performing a Schmidt decomposition, and constructing the reduced density matrix. And then you can define the von Neumann entanglement entropy basically through this formula involving the reduced density matrix for the subsystem A. And basically, non-local entanglement basically means that there is a piece of the entanglement that is not related to the boundary between the systems A and B. Normally, in most systems, the entanglement is an area law, which means that it mostly comes from the degrees of freedom which sit close to the boundary. But the existence of a non-trivial, non-local entanglement basically means that there is a piece to the entanglement entropy which is not associated with the boundary. So, for example, in certain classes of quantum spin liquids, it was discussed by various authors such as Kitab and Pascal that the entanglement entropy, say, in a large linear system, would have a in a two-dimensional system where you apply a cut and area which is in the form of a cylinder, and you try to divide it into two halves. Basically, the area law is this first term over here, but there will be a second term which is universal, which is known as the topological entanglement entropy. And this always comes with a negative sign over here. And the existence of such a non-zero gamma actually means, because the entropy has to be a positive quantity, this means that this quantity S0 can never be made zero. Okay, so this S0 must always be positive over here. And what that means is that you cannot reduce this system by gradual changes, by small perturbation. You cannot turn it into a product state. That's in some sense the definition of a system with non-local entanglement. So in some sense, that is the most important property of a quantum spin liquid, that you must have a non-local entanglement. That is, if you divide the system into two halves, you cannot, by small perturbations, or the wave function is almost as if it's made up of product of stuff that is inside and stuff that is outside. You cannot do that because this S0, otherwise this S0 will become zero. So as long as this gamma is non-zero, that tells you that this S0 itself must always be non-zero.
So experiment really have an access. We cannot have access to
Right. I'm coming to experiments. Yeah. So
that will be
this is for
excitations.
theory. Yeah. This is for theory, basically. Yes. just to complete the story over here, that definition of adiabatically connecting or with perturbations connecting is well defined only for a gap system. But non-local entanglement can also be present in a gapless system. And so there's another class, there's another way to think about quantum spin liquids. And that is basically by using what is called Woods-Wheeler protection. That is, you start with some kind of a fermion many-body state that we are all familiar with, and then project out all the states which have double occupancy, or project it onto the state which has only single occupancy at every side, making it a spin rate function. And in fact, the Fermi liquid itself has non-local entanglement. So if you take such a state, it usually also has non-local entanglement. And depending on what kind of state that you start with over here, you can get different kinds of quantum liquids. Okay, so let me now, any questions about this? So I was so far only basically discussing the definition of a quantum spin. Okay, so let me now talk about the experimental. What are the signatures? How do people look for quantum spin? So first of all, absence of long-range order and large frustration parameter is where you start. Have a material and you want to see if it's a candidate for a quantum spin liquid. You look at what our Ramirez called the frustration parameter. And if the system robustly orders magnetically, then it is probably not a quantum. That doesn't define a quantum spin liquid. These concepts of entanglement and mutual statistics, and these are very difficult to study experimentally. So perhaps someday they could be, but it's really good for looking for spin liquids in a theoretical model, not experimental, at least not yet. A common way to detect something unusual in condensed matter systems is by looking at power laws and temperature, so heat capacity, susceptibility, etc. If you have good theoretical support, then perhaps they could be used. Actually, for example, he likes to discuss many spin liquids, their signatures in terms of various power laws and temperature. But this of course, has two drawbacks. One is that it needs a strong theoretical support, and the second is that it cannot always be distinguished from other effects which could give rise to such power laws, phonons, impurities, etc. The thing that has been the most useful experimentally is neutron scattering. So because a quantum spin liquid has fractional degrees of freedom, it does not directly couple to external probes. By definition, the fractional degrees of freedom, they live within the universe of the quantum spin liquid, and it cannot interact directly with an external probe like a neutron or a photon. It only couples in combinations that are non-fractional, and that leads to, so if a system which is magnetically ordered, we know that the excitation spectrum is dominated by this thing called magnon, which is a spin flip, and it has a well-defined energy momentum relation. So if you did neutron, you'll see strong scattering. If you did energy momentum resolved neutron scattering, you'll see strong scattering along these particular lines. Whereas if you do neutron scattering from a quantum spin liquid that has only spin-on excitation, then the thing that will couple to these excitations are basically pairs of spin-ons, and they will have now an energy continuum. There'll be for any given momentum, there'll be a minimum energy and a maximum energy, and you can have scattering all over the place. And then, depending on the details of whether there's a gap in the spectrum, and where, again, you need theory for this, and which part of the momentum you have low energy excitations can tell you something about what kind of spin liquid. Now, of course, again, these are not unique to this. Again, can happen due to impurities and other effects. So this is also not definitive, but this has been the most useful experimental probe for quantum physics. But more recently, people have been talking about other probes which could potentially be smoking gun signature. So if observed, this would be really dramatic. So I should say that so far we do not, unfortunately, despite intense effort for several decades, we don't actually have a convincing case. So,
solid states.
sorry,
Solid states.
in solid states,
Yeah.
right? Okay, yeah, okay.
Yeah,
Gold atoms,
Yeah,
gold
Rydberg
atoms, yeah, gold atoms and Rydberg atoms. There you have a much stronger case. Yes. So basically, so one proposal that actually came from Kitab, from his Kitab model actually first, is that you could have a quantization of a thermal Hall conductivity. So just like the quantum Hall effect, fractional, you can, if you measure the thermal Hall effect, it could have a quantized response. And in fact, there are claims of observations, but they remain controversial whether this has actually been observed. And there are also a lot of other very interesting claims of spin-on Fermi surface signatures in an insulator. So can you get quantum oscillations in insulators just as we have in metals? As if there is a Fermi surface, even though we are dealing with a spin system where there is no low-lying charge fermionic excitation.
From the theoretical perspective, right? So in the Bush-Miller kind of approach, where you are projecting a
Yes.
fermion wave function, that fermion wave function should have a Fermi surface to begin with.
Not necessarily. So, yeah.
So can you develop a spin-on Fermi surface? You don't start from one.
You mean if you start with a gap Fermi surface?
Yes. Well, insulator you cannot really define it.
Likely, but yeah.
But that is the last statement that you made is telling yeah, in some sense. Signature of
No. I was not saying so. You could start with a many-body fermion state, which could have a Fermi sea, which could have a complete Fermi surface, and then you can project it, do a virtual projection. You can start with a state over here, which is Dirac-like, like in gravity, and then you can project it.
Sure.
Okay, again, it could have a gapless. You could also start with a BCS state over here, in which case you will probably get a gap split. You will not. Well, again, this projection has to be carried out to do it thoroughly, really numeric, because analytical work is uncontrolled.
Right.
Okay. So we don't know exactly what will happen. This is not a,
Even if the input side doesn't have a Fermi surface, for example,
yeah,
like you were saying, a topological instrument, we still have some sort of Fermi surface. Case,
Yeah.
Suppose it doesn't have a Fermi surface, my projection can develop a Fermi surface.
no. I mean, I don't know of any example like
Okay.
that.
So then, how are we thinking about the last statement in this?
No, this statement is saying that we have. This is not talking about any part-on construction. This is saying we are starting with a spin system. There is no underlying electronic charge degree of freedom.
So you're saying this kind of system we cannot approach to the projection.
Yeah,
Okay, so
you can still, even for a purely magnetic system. Sorry, the claim over here is that we are interested in this entire talk about ground states of a purely spin model. But ground state of a purely spin model can be written as a projection operator applied to any fermionic system. Because once you apply the projection operator, you have ended up with a state which is purely spin. So,
So then it depends on which kind of Shire I'm starting.
right,
And then I have to really compare the different possibilities.
exactly. So, what kind of ground state do you have in the system? Well,
Depends on
if you could start, so this is now a guess. This is a variation wave.
this variation.
you're saying that this wave function does not have any resemblance with the actual physical system at all. That's it.
Well, what does that mean? No.
Because in this thing, for getting this electron from the surface,
Yes.
or in an insulator, in a charge insulator.
Right. So
Yeah.
I give you a magnetic Hamiltonian. What's the best variational wave function you can come up with? Perhaps the best variational wave function you can come up with is to start with a Dirac like, you know, a Dirac like Fermi C, and then which will have projected. This is what Patrick Lee and all these people did for a Kagome lattice, and they will call it a Dirac spin liquid. So we don't know what is the best variational state. So the Hamiltonian of the system has only spin degree of.
Only thing is that you have to compare the energy.
You have to compare the energy. There's no other way within the scheme to know what kind of variational state should we start with. Okay, so I'm not saying in this paper, sorry, in this talk over here, or at this in this point over here, that I could start with a state which doesn't have a Fermi surface and generate a Fermi surface. No, I'm saying I'm starting with a spin system. It is a microscopically purely a spin system. There are no charge degrees of freedom. I want to ask what is the best variation wave function. And it may be that the best variation wave function is that you have to start with a Fermi C and then project it. And then presumably the Fermi C remains, but it's now a Fermi C of spin. And it will show interesting quantum oscillations. Again, it's a question mark whether what probes will actually be able to see it. Okay. Will charge probes, will electrical resistivity show it? Will thermodynamics show it? So again, those are all questions. But people have argued that, again, there are experimental claims that they have observed it, but I believe they remain controversial. If you see it in an insulator, then to me this is another really smoking gun evidence for existence of a quantum spin liquid. All right. So, any other questions? So, I'll have to really rush through some of these candidate examples over here. So, I was so far basically discussing what a quantum spin liquid is and what are experimental signatures. So, there are, in my view, 4 main classes of systems that people have focused on as candidate quantum spin liquids, and we're really talking about dimension p bigger than 1, because 1 dimension is quite special in this way of thinking. So there's the Kagome system. This name comes from this Japanese basket weaving. And then there are the triangular lattice-based system, which was focused on by Phil Anderson originally. There are these Kitab honeycomb systems, which several people here are working on. And there are these pyrochlore systems. So these are the main candidates. But given the experimental challenges, it's really important to have a quantitative view. And the moment you discuss a realistic model, such as the Heisenberg model or XXC model, or we talk about the Kitab model, Kitab honeycomb model with other terms, in general, there is really, you have to resort to some kind of computational study. Because without computational study, you can't really have an answer. So what kind of methods are there? There are lots of methods that have been developed. Exact diagonalization of small systems. They can be quite revealing. Quantum Monte Carlo can work well if you can develop a sign problem-free quantum Monte Carlo method. It doesn't usually work when you're looking for a quantum spin liquid. This remains probably the most important method, density matrix normalization group, and I know Manoranjan and his group, they are experts in this, and I'm looking forward to learning more about the use of this method. There are all kinds of interesting variational wave functions with tensor networks and with partons, which are basically writing down the type of variational wave function I was writing and numerically calculating and numerically applying the Kutzwiller projection. There is functional renormalization group and there's series expansions, which is expansions in various parameters. Okay, so let me start with the particular system, Kagome antiferromagnets, and I already mentioned that, okay, Kagome lattice is a lattice of corner sharing triangles. It has very high ground state entropy, and even the classical Heisenberg model on this particular lattice has an exponentially large degeneracy. And in fact, it's one of the few systems where one believes that even the purely nearest neighbor Heisenberg model has a quantum spin liquid ground state. There are not many systems of that type. Usually you have to have multiple interactions in the proper range in order to have quantum. So the difficulty in some senses in getting quantum spin liquid is that there is a very robust method of order by disorder. So even in the most frustrated of cases, very often when you add fluctuations, instead of giving you a highly resonating state, fluctuations end up selecting some kind of order. It's called order by disorder. So basically, let me not go into the details over here, but basically, if you consider the XXZ model, okay, on a Kagome lattice, then various calculations show you the phase diagram that looks something like this. So this parameter here is delta, and this parameter here is spin. And as long as the spin is not 1/2 or 1, the system, despite all its frustration, ends up developing order by disorder. So the only systems which possibly are not not ordered, do not have a conventional ground state, are spin half and spin one systems. And even the spin one systems has been argued to show to break some other kind of symmetry and form some kind of a cluster state. So the only one possibly in this case that has a quantum spin liquid state is the spin half form. And I guess the exact diagonalization is one of the simplest and most important methods over here. So here is a very old work from Claire Loulier's group, which is, in my view, very important. You just look at the low-lying states of a 36-site cluster with periodic boundary conditions of 3 different lattices: the square lattice, the triangular lattice, and the Kagome lattice. And you see the difference. So the low-lying states are very sparse. They are well separated on the square lattice from all the other states. And in fact, these low-lying states over here, the S equal 0, S equal 1, S equal to 2 states, are very well described by what is known as the Anderson Tower of states, representing the spontaneous symmetry. It's one of, in my view, Anderson's prettiest work, really. It's almost a trivial mathematical work, but very, very revealing to understand the concept of spontaneous symmetry breaking. If you imagine a 2 sublattice antiferromagnet, in a mean field model is one where all the spins on one sublattice interact with all the spins on the other sublattice. And you have to put a factor of 1 over n in order to have an appropriate thermodynamic. So this model you can easily solve exactly because it's just total spin on A interacting with total spin on B. So SA dot SB. And you can write down all its states, and you'll find that basically as n goes to infinity, there is a set of states which actually develop 0 energy because they scale as 1 over n. And those states are called the Anderson Tower of states. So those states rapidly actually fall to 0 energy and get separated from all other states, including the spin waves, which can also become gapless, but they are parametrically separated from the Anderson Tower. And you can see that very clearly for the case of the square lattice. You can also see that for the case of the triangular lattice. Now you have to do a 3 sublattice calculation here, but you can predict exactly how many spin 0, spin 1, and spin 2 states and so on will get separated from all the others in the Anderson Tower. In contrast, when you look at the Kagome lattice, you see this very, very dense set of states going all the way down to low energies. And this vertical energy scale also is becoming smaller and smaller. And you don't see any separation of the set of Anderson Tower of states that denotes broken symmetry over here. And in fact, can see that most of the low-lying states are all singlets in this case. So something unusual is going on the Casimir lattice.
So I'm just wondering that in the square lattice, then the system should gap infinity.
Yeah. So right. So this is a finite system. So these states will go down to. So this is where this theory is quite useful. So this is a mean field theory. So in mean field theory, these states will go down to 0 as 1 over n. Everything else is fine. But once you go beyond mean field theory, then these states will develop a dispersion. The one magnon states, and they will go down to 0, but as 1 over square root of n in 2 dimensions. So this is going down to 0 way faster than those. Yeah. So the broken the set of states that lead to spontaneously broken symmetry, they get well separated from all that. Okay. So obviously, when all the low-lying states are singlets, one way one could start thinking about is starting from a different valence bond states and trying to do perturbation. And that's something that we have done with David Hughes. And what you find is that almost any state that you start with, the energies end up becoming very close. Okay? But it's we were suggesting, we were looking for which one is the lowest energy, but actually the energy is further lowered. This is what the DMRG work shows. The energy is further lowered by about 1% or so relative to any one of these, basically by resonating between the different states. Okay, so again, without going into the details of the calculation, this was a work done by Steve White and collaborators. They did DMRG calculations on cylinders of finite width and argued that the whatever we were getting for isolated valence bond configuration by using perturbation theory, the actual energy of the resonating state was much lower than that. And they argued that there is actually a gap in the spectrum, and this is an example of a Z2 spin liquid. However, this remains controversial. There have been several papers since then, some arguing that there is a gap, some arguing that there is no gap, and some arguing that it's actually a Dirac spin liquid, others arguing that it's a spin-on Fermi surface. So all kinds of arguments are there. So these issues are not easy to definitively settle from numerics.
Because I think the numerics is restricted.
Is restricted, and yeah. So the problem is that once you start to get something gapless, then there is a very large entanglement. And so most of the methods, they rapidly reach their limit.
So let's say JLR.
Yeah. So yeah. So unfortunately, let me not go into the details over here. But currently, most people, if you ask people what is the favorite state that people think for the Kagome lattice Heisenberg model, favorite one is one of Dirac spin liquid. And they argue, these authors here argue that the reason why people see a gap state, Dirac spin liquid is very special because you have gapless points only at very special points in the Brillouin zone. And if you wrap it around, just like in case of carbon nanotubes, you could miss the gapless point. And in fact, they argue that if you apply a flux over here, you can start to bring the gap down. Really close the gap all the way is not clear. But anyway, most people believe that perhaps the lowest energy state is a Dirac spin liquid. But I think again, interplay with experiments is important. And there are the material that garnered the most interest are these Hubbard-Smithites, which are really structurally perfect Kagome layers. And we know that there's an exchange constant of order 200 Kelvin, but there is no long-range magnetic order with a frustration parameter, if you like, at least of 10,000. So it's a good case over here. Also, if you look at the neutron scattering structure factors, you see features that can be mimicked in theory. Okay, so this is a comparison between experiment and theory. The problem really is that almost all kinds of calculations can give you these kinds of features. Okay, this is a calculation from Sudhir Sachdev's group arguing for a gapped spin liquid, but there are other calculations with Dirac spin liquids which can also get very similar structure. So the point is, no matter what you do in the Kagome lattice, you'll find that almost all, this is the Brillouin zone over here, almost all the scattering is at the zone boundary over here. There is almost nothing over here. And the nearest neighbor model shows maximum at these points in the middle of these zone boundaries, basically.
On top of that, the Sinon Fermi surface.
Yeah.
So that would be a signature.
That would be a signature. That would be gapless.
Yeah, I mean,
Then
that's what
that
I'm
would
asking.
mean that it should
Yeah.
be gapless.
Yes.
So is this gapless or is this gap?
Yeah.
So that question, that's a very important question. The problem really again is that any real system is always disordered. And this material, even though it's structurally perfect, it has this thing called antiscientism. So some of these Kagome layers are separated by these extra what I call triangular layers, which are supposed to be zinc and non-magnetic, but some of the zinc is replaced by copper. And if that happens, then you can get gapless excitations from these guys. And can they actually change the properties of the system? So that's not so obvious. And again, I could just discuss the system in great detail, but basically, people have done all kinds of clever measurements, including NMR and neutron scattering, and they have argued one way and another way. They have argued there is a gap and there is no gap, and the physics due to the coupling with these extra springs does not affect the underlying spin liquid, but nevertheless the overall status remains good. It's not clear whether there is a gap in the system or not. So despite all the efforts, we don't know whether a Kagome lattice, this particular experimental system, the Hubbard spin heights, actually have a spin liquid, and if they do, what kind of spin liquid? Okay. How much time do I have? Should I just wrap up basically? Okay. I would just say that I was going to talk about the triangular lattice system again. Most people, almost all numerical studies argue that there is a ordered ground state, but you can frustrate the system even further by adding a second neighbor interactions, and that can lead to a spin liquid state. Again, what kind of spin liquid state? The question. There's a recent paper by Joel Moore, for example, arguing that it's actually a Dirac spin liquid. Again, there are people who disagree with that, and experimental situation is also, in my view, unclear. Again, the impurities are always important, and in this case now there are a lot of very interesting candidates. There isn't just one or two, but there are many materials which are good spin-half triangular lattices. But all kinds of proposals have been made from the experiments, but nothing definitive. And the third system that I will not have time to really talk about over here, but let me just mention it. And I know there are people who know more about this than I do over here. They're working on this system. They are the Kitab models. Again, Kitab very cleverly invented another model where you have purely Ising interactions, but the Ising interactions on this honeycomb lattice involves X, Y, or Z degrees of freedom along the three different bonds over here. So only X interactions, XX Ising interactions along all these bonds, YY along these bonds, and ZZ along these bonds. It turns out that this model is also exactly soluble. It has fractional excitations. I will not go into the details over here. It basically has a phase diagram that looks like this. You can have gap spin liquid or gapless spin liquid. The excitations are Majorana fermions as well as what are called Wisons or flux degrees of freedom. And they have all kinds of interesting experimental signature. And even more surprisingly, there are materials which are claimed to be dominated by cation type interactions. And basically, again, unfortunately, the systems always order magnetically, at least in zero magnetic field. So at best, one could say that they are near a quantum spin liquid phase. And so perhaps by having a magnetic field or some other parameter, they can be turned into a quantum spin liquid. And this is the most dramatic claim of all by Atsuda's group, that they actually see a fractionally quantized thermal Hall effect. So there is a claim that if you take this particular material, ruthenium trichloride, and you measure the thermal Hall effect, that is, if you measure the thermal conductivity where you have a temperature gradient in this direction over here, and you measure the heat flow in this direction over here, the conductivity divided by the temperature is quantized just like in the quantum Hall effect, except that the E square is replaced over here by the Boltzmann constant square.
But isn't it even this experiment?
This experiment is extremely controversial.
Because it's so much sample dependent.
It could be sample dependent or it could just be wrong. Because other people claim that this is simply not true.
Because the stacking of ruthenium trichloride actually depends on what kind of sample it is.
Okay, so that's one possible explanation, that everybody's experiment is correct, but the results are sample dependent. That's one possibility. But another possibility is that this is a very hard experiment. Let me say, if people have not heard about this, why compared to the fractional quantum Hall effect of the charge variety, this is a really difficult experiment. So when we talk about the quantum Hall effect or the fractional quantum Hall effect, that has a longitudinal conductivity which is zero, okay, and the transverse conductivity which is 1 factor. And so basically what happens is that if you look at the voltage along any one of these paths over here, okay, that is going to be the same everywhere along this line over here. From this edge, it will be the same, and there'll be a voltage difference between these two. Then it is easy to measure the voltage. But in this case, in real materials, you have phonons, you have other degrees of freedom, and the longitudinal conductivity is hundreds of times larger than the transverse conductivity. So being able to, that means that you not only have a temperature gradient in this direction, you also have temperature gradients in that direction. And so being able to measure the thermal conductivity accurately is extremely difficult. And so there are a lot of measurements and by very prominent Swanong and any other groups that try to do this experiment. Claims that it is quantized or not quantized. Okay, so let me come to my summary over here. So the study of quantum spin liquid is a rich and mature field. These are examples of macroscopic quantum phases. They have very interesting excitations, which could be anyons or fermions in a purely spin system. Most important thing is that they have long-range entanglement that is necessary in order to support exotic excitation, fractional excitations. And I didn't even talk much about emerging phase. Soluble models are very helpful for illustrating the what spin liquids are, but realistic models for experiment, they require computational studies, and again, it's not easy to have a definitive answer. Experimental materials candidates are there. People have thought of lots of interesting signatures, but there are always subtleties, and so far, unfortunately, we do not have a definitive quantum spin liquid phase in here. So, unfortunately, I have to stop on that negative final conclusion. Thank you.
So, I thought and now local first question. You lost this slide. Conclusions. And this one, is it something related to durable friendship?
No, this is simply if you have one-dimensional fermions, just like in the quantum hologram, you have edge states. Basically, the current that they transport is very simple. Basically, it is proportional to how many states are occupied, and the voltage difference or whatever depends on what is the potential of how many more are occupied on this side versus this side. So for any normal system, you will find that if you have edges on this side and this side, this Q will always turn out to be a negative. Q is a fraction, let's say. If you calculate it for some one-dimensional, so imagine that you have an insulator in the bulk over here, and you have some kind of a gapless state over here, some kind of a Fermi sea over here.
Here, thermal conductivity is also proportional to T.
It will always be proportional to T. So that divided by the temperature will turn out to be basically an integer times this factor. So the prediction in this model, in the Kitab Model model in a magnetic field, is that this factor is 1, which is because these are from Majorana fermions. They are Majorana fermions, and Majorana fermions have the property that the left and the right side is identified.
And then together they have ups.
If you combine two Majorana fermions, yes,
Then the ups.
yes, yeah, they don't have a proper Hilbert space associated with this.
Yeah. Maybe I have one question last slide. So yeah, it's a bit of technical question. Is there modeling normal setups? This hot and cold ends. These are applied by the experiment or is it generated?
I think they are generated. Yeah,
Generated,
you drive.
Yeah.
I think the way the experiments are done is you drive a
Current in the longitudinal direction.
you drive a current in this direction over here, and you will see that there is a
Because they are not carrying charge, they
Right.
create a
They will
thermal.
create
So that's a generated.
that is the way experiments are.
Quick question. Yeah. That's structure one to how this the region of one.
Sorry,
Structure, how do you, conclude that decision?
yeah. So again, back to this one here. So basically, you need a bit of clear. So different. First of all, structure factor can tell you whether there's a gap or not, right? And secondly, it can tell you where in momentum space are the low energies. So usually, different types of quantum spin liquids either have a gap or no gap, and they have low-lying excitations at different parts of the momentum. And you have a continuum, right? So if you have all those three features, that's a strong indicator that you don't have Magnon-like excitations. Your excitations are fractional, and you have low-lying degrees of freedom at these points. Maybe you have an entire Fermi circuit. Maybe you have low-lying excitations everywhere. That would be a Fermi circuit.
But these are dynamic structure.
Dynamic structure.
At least excitation is multiple quasi-particle.
Well, what does that mean? They cannot couple to external probes.
Yes.
They are well-defined quasi-particles in the sense that they can be well separated from each other, and you should think of each one of them as individual quasi-particles.
So if I understand the continuum,
Yes.
this is because they cannot couple to the external probe that we can provide.
Exactly.
But theoretically speaking, they will carry a proper dispersion.
Yeah. I mean, in the Kitab honeycomb model, Majorana fermions are, you can really write down the state in terms of these Majorana fermions. Right. But they cannot couple to external.
Yeah, so that's why the continuum is getting
That
there.
is why they continue.
I think let's stop here. Okay, one more. I should ask the online. Online audience, do you have any questions? Sorry, voice is also not very clear. So anyway, so yeah.
Some question.
Anyone else?
There's something in the chat.
Oh, there
box.
is something in chat box. Sorry, it was not video. Okay, I guess it's. So if it is not, let's thank Professor for giving that. So next talk will be in ISCS at 4 o'clock, and third talk is going to be here again. Thank you very much. He is outside. Please help yourself.